If you've been following our channel, you'd know that we've created detailed playlists on multiple topics related to supervised learning, unsupervised learning, probabilities, data preparation. For the absolute beginners, we are creating a playlist which is called Dare to Learn Python. So in this video, we're going to continue to talk about NumPy, and this is part 2 of the tutorial. A couple of interesting functions that you might have seen at different places, those are also available in NumPy. So for example, if you want to see the value of exponent, which is the Euler's constant. If you mention the power as 1, it'll give you the value of the Euler's constant. If you write this as 2, it'll square that value of Euler's constant. So this value is 2.718, goes on, right? Similarly, if you want to apply the exponent function on an array. So we are creating an array 4, which is a NumPy array, has these elements as 6, 4, and 7. And if we apply exponent, it will be e raised to the power 6 as the first element, e raised to the power 4 as the second element, and so on. That's how it works. Here's how the calculations happen. Now, similarly, there's a logarithmic function. If you want to find the log of a number, by default, it will be log to the base e, which is the Euler's constant. But if you want to customize it, you can also change it. So we say log 10, and we mention log 10 of 8. It'll compute that. Let's see both the values. So this is the value to the base e. And if you want to change this to 10 here itself and change the value and check what happens, this is a different value. Similarly, if you want to run this for the value 8 and base 10, this is how we get the output. Now, there are operations on arrays that can also be performed. So if we have two lists here, 1, 2, 3, 4, 5, 6, let's see how lists would react to it. We are doing L1 plus L2, and this is just concatenating the two lists. But what happens when the same elements are converted into arrays, two separate arrays? L1 is represented as array 7 here, and L2 is represented as array 8 here. And if we perform addition or arithmetic operations, let's see what happens. So if you notice, it's performing all those operations element-wise. So when we performed addition here, it's adding element-wise. 1 and 4 leads to 5. 2 plus 5 leads to 7. 3 plus 6 leads to 9. When we do subtraction of the array 7 from the array 8, you see a constant difference of 3 between the elements. So you get 3, 3, 3 here. When you do multiplication, you simply get the product. When you do division of array 7 by array 8, so you can see 1 by 4, 2 by 5, and 3 by 6. That's going to be 0.25, 0.4, and 0.8. Element-wise operation again. If we do an inverse of an array, it's going to just put all these values divided by the elements of this array one at a time. So 1 divided by 1 is 1. 1 divided by 2 is 0.5. 1 divided by 3 is 0.33. It's assuming there's an array which is 1, 1, 1, and you're dividing by a known array which is 1, 2, 3, and that's how it's performing the operator. Similarly, if you want to raise a power, so let's say we say that array 7 raised to the power, this 2 asterisk signs essentially represent exponential. So we are raising each element of array 7 to the power corresponding to the element at the same index in array 8. So 1 raised to the power 4 will be 1. 2 raised to the power 5 is 32, and 3 raised to the power 6 is 729. That's how we're getting the value. We can similarly perform operations on two-dimensional arrays. So the example that we looked at here were one-dimensional arrays, but can we do it for two-dimensional arrays as well? Yes, we can do that. So we are generating a matrix called matrix 7, which has 9 elements from 1 to 9, because np.arange, remember, doesn't include the upper value. So values from 1 to 9 in sequence, and we're converting it to a 3 by 3 shape. That's matrix 7. And we are generating another matrix, which is matrix 8, which is an identity matrix. Just some time back we discussed, it'll be a square matrix of 3 cross 3 dimensions here, because we're giving the input as 3. The diagonal elements of which would be all 1s, and the off-diagonal elements would be all 0s. Let's run this. So this is how you get the output. Now we are trying to perform various operations. Can we simply add these two matrices? Let's say we do matrix 7 plus matrix 8. It is going to perform the addition element-wise. Let's run this. So if you see, 1 plus 1, that's the first element here. 2 plus 0, it's going to be 2. 3 plus 0, it's going to be 3. That's how it's adding all the elements. Similarly, it's doing subtraction. So 1 minus 1, it's going to be 0. Let's just consider the first row here and first row here. So 1 minus 1 is going to be 0. 2 minus 0 is going to be 2. 3 minus 0 is going to be 3. So on and so forth. Multiplication. So notice, it is doing element-wise multiplication, but if you studied matrices earlier, you would realize this is not necessarily the matrix multiplication. That's done through a special function. We'll talk about it in some time. But let's just understand the element-wise multiplication right now. It's going to pick the corresponding elements of the second matrix and multiply it with the first matrix, and that's how it's performing the operations. So is the case with division. So let's say if we look at this element, here it's 5 and here it's 1. So when we do division, it'll still be saying 5. But what about other values? Values where you have a number, a finite quantity in the numerator, but the denominator is a 0, you know that leads to infinities. And that's why it gives you a warning for that. Essentially, it says that you probably made a mistake. You've done a division by zeros. Now, if you want to do a proper matrix multiplication, like the way matrix multiplication is defined, we can just generate some numbers and show it to you again. So let's say we generate a similar matrix, again, a 3 by 3 matrix. It's identical to what we generated as matrix 7 sometime back, and maybe a different matrix, which is values from 11 to 19, again, a 3 by 3 matrix. So again, 9 elements, and that's how it is. So this is matrix 9 and matrix 10. And if you want to do a proper matrix multiplication, you would use the @ symbol. If you just put an asterisk, it'll be a simple element-wise multiplication. So we just run this, and this is a proper matrix multiplication. If you've studied that, you can validate it by doing the calculations yourself. Similarly, we can do dot products. So if you've studied vector algebra, you'd probably know about dot products. It's going to do element-wise multiplications and do a sum total. So 1 into 4 is 4, 2 into 5 is 10, 3 into 6 is 18, 4 plus 10 plus 18, that's going to be 32. That's the outcome you get. A lot of times you'll be needing this in Python when you're calculating the similarities between the observations or objects and you're doing clustering. This calculation comes very handy there. Can we transpose an array? Actually, very simple to do that. You can simply create an array. Let's say we created a 2-dimensional array and we just use a .t and it'll swap the rows and columns. Let's just run this. So this was a 2 cross 3. Now the output is 3 cross 2, 3 rows and 2 columns. A very popular method in NumPy that's known as ravel, and it's often used while working with different data sets and images to flatten the data. What's the use? You may have a multi-dimensional data and you want to bring it to 1 dimension. Ravel comes very handy for that. Let's see how does it work. So we are creating an array which is 2-dimensional. Essentially, it has 2 rows and 3 columns. But if we do a dot ravel and give this input, the original array, as an input to the dot ravel method, let's see what is the output. So the original array was 1, 2, 3, 4, 5, 6, 2 rows and 3 columns. When we did ravel, it converted it to a 1-dimensional array. So we have specific inputs here to decide how we want to get the flattened output. By default, it's going to go by the row. For example, it's counting 1, 2, 3, and then it's putting 4, 5, 6. But if we give an additional input here, which is, let's say, F, this is essentially for columns, let's see how the output would look like. So see, now it's creating the flattened output going by the columns first. So 1, 4, 2, 5, and 3, 6. That's the only change. There are some additional functions, basic calculations that we can perform. So if you have an array, you want to add all the elements, you can do a dot sum. That'll print the sum of the elements. If you want to calculate an average of all the numbers that you have, you can just simply use np.mean. All these functions that we are talking about here are directly usable in pandas as well, which is a very popular library for data science, essentially working with data frames. So because it's built on top of NumPy, all these will come very handy when you're dealing with features, essentially in a spreadsheet like data. Similarly, if you want to find for an array, what are the minimum or maximum values, you can simply use np.min and np.max. Now, a lot of times we want to perform experiments with our data. We want to generate some numbers randomly. And NumPy has a whole bouquet of such methods which allow us to generate different kinds of random data. And we are saying it'll be called from the random module of NumPy using a specific method called randn. Now, this will give us an output which will be as per the standard normal distribution. What is a standard normal distribution? Data which has a mean 0 and a standard deviation 1. So this output would follow a specific distribution. So in this function, we only gave 1 input, which means it gave us an output which is 1-dimensional. It has given us 5 elements. That's in a 1D scenario. But if you want to generate a 2-dimensional output, we can give the number of rows and number of columns separated like these, and it'll generate the output as per the function. Notice there's a difference. Earlier, we generated the output using randn, and the values were following standard normal distribution. But when we just write rand, it generates values between 0 and 1, where 1 is not inclusive. Let's see. It's generating these values. 1 is not included. It's generating the output in a format which is 3 rows and 3 columns, but all the values are between 0 and 1. So you have to be careful about which specific method of the random module you're using. If you use randn, that is something different. If you just use rand, that's something totally different. Similarly, we have a randint method as well. which, as the name goes, you generate some random integers. And it can accommodate several other inputs, like you can mention the smallest value, the highest value, and how many values you want. So when we give np.random.randint and we write 1, 5, it means 1 is the smallest value. It's exclusive of 5. So it'll go up to 5, but will not include 5. And we are generating 10 such values. It's not something that's dividing the space in these many values. It's generating values between 1 to 5, 5 exclusive, 1 inclusive, and 10 such values. So you see, some of the values are repeated, of course, because between 1 to 5, you only have 1, 2, 3, and 4. Out of those 4 values, you get to get 10 outputs. That's how it goes. Now, if you want to generate a matrix-like output, there's a slightly different syntax here. You use the same identical randint method. You mention the smallest value, the highest value, which is exclusive. So you'll go up to 9, and you want a 5 cross 5 matrix. This is how the output is going to look like. You might be wondering, there are times when we're writing print, there are times we are not writing print. Let's see what happens when we don't write print and we run this. So you see, it just tells that this is an array. If you write print, it will not show that this is an array type. It's kind of understood, not much of a difference. But you might have noticed that by running this again, the numbers got changed. Note, all these values that we are generating are random. So if you repeat the same line of code, you may not necessarily get the exact same output. It's a random instance at the time when I'm running it on my machine. When you run it yourself, you may get a different output. For example, if I just refresh this now, so you can see this matrix has 6, 4, 8, 6, 2. And if I refresh this, you get some different values here. So because it's random, it's going to change every time. Once again, if you want to generate a random array, we want to do some experiments with it. Let's say we generate an array, which is a unidimensional array or one-dimensional array with 10 elements, and they follow a standard normal distribution. Let's do this. And now if you want to access specific elements of it, pretty much the same way. You can access the element at index 6, which will be 0, 1, 2, 3, 4, 5, and 6. It should be the value that it gives. So you see 0.686, 6886. That's the exact same value that we have here, right? Similarly, if you want to apply slicing here, we sometime back discussed starting index and the upper index, but upper index is not inclusive. So starts from index 4, which means 0, 1, 2, 3, and 4, negative 1.669, and goes up till 5, 6, 7, 8. That's it. The index 9 is not included. Let's just run this. So you can see started from negative 1.66, but went up till the last but one value, or the second last value. That's it. If you want to check it for multiple indices as input, so we can give a combination of NumPy functions, like we can use np.arange to choose the indices, and then filter the random array we generated using these indices. So we are selecting some index values, which are from 3 to 10. Of course, 10 is not inclusive. So you can say from 3 to 9 with a step size of 3. What will these values be? These will be 3, 6, and 9, because your step size is 3. So from 3, when you start, add 3, you'll reach 6. Another 3, you'll reach 9. 3, 6, and 9. It's going to get the values at index 0, 1, 2, 3, then 4, 5, 6, and then 7, 8, 9, the last value as well. Let's just run this, and you can validate. That's the exact same output you're getting. 0, 1, 2, 3, this is the value that we got as the first value. Then 4, 5, 6, this is the second value, and the last value, which is the index 9. So on the same array, if we want to apply some logical operations, we can do that as well. Let's say this is an array we generated some time back, and if you want to segregate the positive and negative values here, so if you apply a logic, when you do a greater than or less than sign, it's going to result into a true or false for every single element. So it's going to put a true for every element here, which is greater than 0, and a false for everything that's less than 0. Let's see. Rather, I should say everything that's not greater than 0, it's going to put a false for it, inclusive of 0 as well, right? So this is how the output is. And now if we apply that as a filter, we can segregate the positive and negative values from our original array like this. So first is a filter which shows all the values greater than 0. Last is a filter, all the values less than 0. We did not have anything exactly 0 here, else that would have also come under the values less than or equal to 0. We could have written it that way. Similarly, we can access the entries within a matrix. We saw that some time back as well through an array. So let's say this is a random matrix, 5 cross 5 matrix, which has all its elements following our standard normal distribution, and we are trying to access its elements. So if we just write 1, what does it mean? It simply means that we are trying to access the row index 1, which will be the second row. And if you mention like this, 1, square bracket 1, square bracket 2, or just square bracket 1, comma 2. That's one and the same thing. It's going to access the row 1 and column 2. What do you think it would be? Row with index 1, which is this row, and column with index 2, 0, 1, and 2, this value. Let's see what we get as an output. Let's check the first one, which gives the entire row. Let's check the second one, 1, comma 2, and there you go. Both the approaches give the same answer, whether you write it as square bracket 1, square bracket 2, or just 1 square bracket 1, comma 2, that's giving the exact same output. Essentially, the row index 1 and column index 2. So they intersect here. That's the value that you're getting. The random array, we are once again printing it, and we are trying to apply a filter on the positive and negative values. Let's see what happens now. What will be the dimensions of the output? That'll be interesting to see. So let's see if we filter it for the values greater than 0. Would it retain these dimensions like 5 cross 5? Let's see. It actually filters the values and returns those values to you without retaining the dimensions. So it's giving us a collection of all positive values and all negative values, essentially in a one-dimensional output. We're just printing these again just to refresh what these random matrices or arrays were, and we will try to perform some operations on those. So let's just say we come to this one and we want to make some changes. We want to select a small portion of this matrix, which will be row indices 1 to 2. The upper value is not counted, right? So index 1 and 2, 3 and 4, because 5 will not be counted. So let's first understand what are these. Index 1 is this and 2 is this. We are talking about these two. And now we are saying we want column indices 3 and 5. 0, 1, 2, 3, and 5. So we're referring to these last values here. Let's see what happens. What is the output that we get? So this was an operation on a sub-matrix of the original matrix. What we've done is we've converted these values to 0. So what are the values that are going to get affected? This 5, 6, and 5, 4 is going to get converted into 0. Let's just ignore this for the time being, and let's just print this as the output. What is the output that we get if we take a subset of the original matrix? This is what we are trying to print. So this is the overall matrix, and now it prints 0 by 0. Why? Because we've already casted it to 0. If we want to print the overall output, so let's just put this as 0, run this again. The original matrix has also changed. So earlier the matrix, if you see, was showing some values here, 5, 5, 6, 4. After we casted and we looked at the output, it got changed. It also affected the original matrix. The random matrix 3 has been modified. Let's say we want to extract some specific portions of a matrix. So we want to just select the first two rows. Index 0 and 1 would be counted. 2 would not be counted. Index 0, 1 would be counted for the columns. What will be the output? If you're wondering which matrix is this was a matrix that was a collection of the standard normal. It has just selected these specific rows from that. Let's say we want to change all the values in a matrix to 3. It's going to override and change all these values in the sub-matrix to 3. Let's see what happens. So you see now all the elements are 3. But now what has happened to the random matrix, which was a collection of the numbers which were following a normal distribution? Would that also change? The answer is yes. You can see this portion of the original random normal matrix has also changed. If we don't want this behavior, if we want to take a smaller set of the data, modify it, but we don't want the larger set of data to get modified. In data science, we need this a lot of times. When we're working with data, we want to modify a certain portion of the data as an experiment, but we don't want to affect the source. If that is the case, let's try to see how we can handle it. So let's generate a random matrix, which is a collection of values which follow a standard normal distribution, and it's 5 cross 5. And then we are saying we take a copy of it. So we are again doing the sub-matrix thing exactly the same way, but this time we are making a copy of random matrix and then doing. When you make a copy of it and you make modifications on the sub-matrix, it would not be affecting the original matrix. That's the takeaway. So you see what we did. We took a 5 by 5 matrix, which is this. We said we want to take a sub-matrix out of it, which will follow index 0 and 1 for rows. So it will take these two rows, and 0, 1, and 2. 3 will not be counted, but up to 2 it will be counting. So 0, 1, and 2. So it will take essentially this entire portion from this 0.55 to this value as the submit. We are saying all these values need to be changed to 3. So it's going to change these to 3. If we print it, it's just printing the output as 333. But now if you print the original matrix, it is unaffected. Last time, since we did not create a copy, it had affected the original matrix as well. That's the takeaway. Now, there are a couple of other statistical functions. Just like we saw other functions like sum and mean, we have other functions as well, like we can take a median, and all these are common functions that we'll be needing day in and day out when working with numbers. So we can get the median value, If you want to get the standard deviation of the data, you have a .std for that. All these are basic NumPy functions which are available. Likewise, if you want to calculate the variance, you have something called as np.var. Now, if you want to search a NumPy array for a specific condition, we've already seen a similar condition that we could apply. So earlier we used something called as a logical subsetting to an array. We passed something like this. We used to write like array, and we were writing wherever the array value is greater than 2. This is not the same. This is somewhat different. What are we doing here? It's going to essentially return the indices. This np.var is going to return the indices of those elements in your array which are greater than 2. So what are those elements? Of course, 3, 4, and 5. And what's the index here? 0, 1, 2. That's the index. It's not returning the value. It's returning the index. What's the index of 4? That's 3. What's the index of 5? That's 4. It's returning the index, whereas this used to return those elements which were greater than 2. This is the difference between this filtering and np.var. np.var returns the indices of the values that satisfy a particular condition. Likewise, we have some important functions related to sorting in an array. So let's say we have an array which has these elements and not necessarily in an order. If you apply a dot sort on this array, what happens? Let's see. So by default, it's going to do an ascending sort. Starts from the smallest value and goes to the highest value, like this. Similarly, we have something called as an argsort. What is an argsort? Argsort is essentially going to give us the index of the values once the array has been sorted. So let's understand this. So we have these values, 5, 3, 1, 4, 2. These are not sorted right now. But when we say argsort array, this is going to return the index of the values as if they were sorted. Let's see what happens. So you can see it's saying 2 as the first value. Is that the smallest value in the data? 0, 1, and 2. That's the smallest value. Then it's saying 4. So after 1, the value in the array should be 2. Where is that placed? 0, 1, 2, 3, 4, 4. Then it's saying the next value, if we would have sorted these as 1, 2, 3, 4, 5, the next value after 1 and 2 would be 3. Where is that located? Index 1. So it's returning the indices, whereas this returns the sorted array. That's the difference. For example, let's just take these numbers, 40, 10, 30, 20. So let's say this is the array, and if we imagine sorting it, we can write it as 10, 20, 30, and 40. This will be the sorted order. What are the indices of these values? What is the index of 10? That's what argsort is going to return. Index of 10 is 1 in our case. What is the index of 20? Index of 20 is going to be 3 in our case. 0, 1, 2, and 3. What is the index of 30 that comes after that? Index of 30 is going to be 2. And what is the index of 40, which comes as the last element? That's going to be 0. So this argsort is going to return the indices like this, 1, 3, 2, 0. If we want to reorder the elements in a multi-dimensional array, we can do that as well. For example, let's say we have an array which is 3 rows and 2 columns. So we have a list of lists. Essentially, you can imagine these are 2 column values for each row. That's how it is. And we are saying we want to apply argsort on the index 1, the second index. So which means we want to sort this output by the column indices, which will be the second column, 4, 2, and 6. And that's being given as an input to the matrix. So we are getting the argsort, which is nothing but the index of the second column, which is 4, 2, and 6, as if they were sorted. And then we are giving it as an input to the matrix. Let's see what is the output that we get. Let us see. 4, 2, 6 has been sorted to 2, 4, and 6. And the other values have also been sorted accordingly. So 1 and 4 was the first row. But after you did a sort on the column index 1, 3 and 2 becomes the first pair, then this one, and then the last one. Now, finally, if you want to save an array, we can always save an array using np.save. It'll be saving the array to the specific working directory where you work. Let's say we show it to you here. Right now, you don't see anything. And if I just do a np.save, what happens? You can see it has saved an array which is called myarray.numpy. This is the name we gave it. And it contains what all elements? It contains these elements. If you want to load an array that you've already saved, let's say you're working on some numbers and you save them, but now you want to work on them again. So you can use np.load. It's very simple. You can just mention np.array. You can just mention the name of the array, .npy. .npy is the extension. So this will have loaded the array and we can continue to work on this. All right, so that was a quick walkthrough of the NumPy array, the most popular and fundamental library of Python, which we are going to use rigorously throughout the course. And that's why it's important to get familiar with it. A lot of the steps that we've done today might not make complete sense to you because these are being done in isolation. We've not really performed these actions on a real data. But trust me, this comes very handy as you start working on the large data sets as well, including the advanced areas where you talk about working with images, computer vision, etc. So keep practicing, and if you're comfortable with these basics, it should be a good starting point. We'll be covering other libraries like Matplotlib, Seaborn, and Pandas in the subsequent tutorial. Thank you.